Yes, please.
Sir, you uh, lab report submission would be on 22 March, right?
Yes.
Actually, sir, what I have realized is the date that you feed on Moodle. You say 22 March 12, sir, which becomes effectively 21 March 11:59 p.m.
Oh, I didn't even check the time. I'm so sorry.
Yes,
So,
sir. So, sir,
just send me a
yeah.
reminder today after the class, and I will change it to 23rd. And please ask everybody to submit. Is that all right?
Yes, sir, yes, sir. Thanks.
Okay. So now let us solve with some questions, and then we will go ahead and do more complex stuff. I mean, I taught this in the class, as a matter of fact. So there is really not Priya, your argument is not really correct in the sense that King Altman, at least all of you should have been able to do, because this is exactly what I taught in class. I said you have a reaction A plus B going to some product P, and then you could have C plus D as well. And as I said, therefore, the enzymatic methodology is E plus A goes to some EA, and then EA plus B goes to some EAB, right? And then this EAB sort of, if it is irreversible, there is only one direction here, it goes to E plus B. This is an ordered reaction. This is a bi-uni reaction because this is bi 2 and this is uni product 1. You could have a bi-bi reaction, in which case you would have had P plus Q. But we didn't have that. So I'm sort of making a generalized answer so that you know how to handle King-Altman. And the King-Altman method is to look at this and at this and at this. There are only 3 nodes here because this is what it is. And so we can have the 3 nodes here, E. And so there is a methodical method of doing this. And you have EA, and you have EAB. And the forward reaction to this is K1A. The reverse reaction is K minus 1. The forward reaction here is K2B. The reverse reaction is K minus 2. There is only one reaction here, K3. There is no reverse. If there was a reverse, then would have drawn a minus K3 line. This is all that you have to draw in terms of reactions. And so the 3 things that you have, and so you follow the King-Altman methodically. This is a triangle. So you have 1 where this arm is missing, 2 where this arm is missing, and 3 where this is this one, which is where this arm is missing. So for E, you have the following. Can you now tell me? E is sitting here. E is sitting here. So let us do this very, very peacefully, because I think we should solve every problem. E is sitting here, which means E is sitting here, which means E is sitting here, and which means E is sitting here. So for E, what are the 3 things that are there? So for E to be made, this one here, to reach here, you would need to go like this and like this. Okay, sorry. So there has to be a proper. Can you all see this? And for E to be reached here, this has to go like this and like this. And to be E to be reached here, it have to go like this and like this. So how do you reach E? You reach E by this and this. Now this is here is K2B, K3. K2B, K3. K2B into K3 is one method that is taken care of this. What about this one? K3, K minus 1. What about this one? K minus 2, K minus 1. These are the 3 methods of reaching E. the back one here, K2B, K3. The E here, the K3 into K minus 1. And this one here, K minus 2, K minus 1. Now, let us concentrate on EA. That is this one. So we rub this one out. Let us do it very, very peacefully and slowly because that is the only way I can make it out. Now EA has sorry, is here. EA is here, so you can reach it like this and this, which is this and this. EA is this and this, which is this and this. And EA is this and this, which is this and this. Off here, off here, off here, right? Does that make sense? Okay. So now, what about this one? ठीक है? कुछ मिस कर दिया मैंने? हाँ. तो EA, let us look at this one. This is K1A, K minus 2. The first one here. K1A, K minus 2. I mean, I'm sort of repeating this because I did this in the class and I noticed that. Okay. We'll do these problems one after the other. Not only these problems, but all others as well. K1A into K minus 2. K1A, K minus 2. That is number one. What about this one? Now, this one does not exist. So this one does not exist. This part does not exist. So this is gone. But this one exists. K3
into K1A.
plus K3 into K1A. And then what about EAB? So EAB is sitting here. So let me rub this out. What about EAB? EAB is sitting here. Sorry. EAB is sitting here. So we have this and this. One. Then we have this and this. This is 2. And then we have, see, this one is gone. This one, bottom one gone, which means this and this. All of these ending up here because this is the EAB. Now what about this one? This one does not exist because this is K3, so this is 0. What about this one? This one exists. EAB is K1A, K2B. K2B. And what about this one? This one also does not exist because so only this one. This is something which I had pointed out in the class. So we have now the reaction velocity as V by V max, which is the same thing as EAB, because EAB leads to all the products, upon the sum of all these, the sum, it's often called the. Can all of you hear me?
Yes, sir, we can hear it.
Okay. The delta, which here is equal to K1, K2, AB divided by all these things taken together. So notice that there is a B term. There is a B term here and some of this, and there is an A term here, and there is an AB term here, and there are some constants. And so I really don't need to bother about it. I can put all the constants together as some K and all the constants capital K into A, all the terms containing A, and I can put all the constant terms K2 as B terms B. There's only one B here, so it's not really important. And then some. And all the AB terms like this in some constant if K3 AB. And this is also some constant K star, whatever. This is actually the same as K3. And so my reaction velocity will be of the form some constant or Vmax or whatever, AB, because it will all cancel out, AB upon some K plus K1 plus K2A plus K2B, K3B, K3B plus K4AB. That is all that we had to do. And this is something which I was half taught in the class. So I do not know whether you people were able to solve it, but it is not a difficult problem to solve. It is only King Altman, something which has been done in class. It's an easy problem. Suppose you had 4, if you had P plus Q, then you would have many more parameters, and of course, and suppose you have 3, and suppose, so you have to look at King Altman in a very methodical way and actually be able to derive these expressions. Okay, so this is how you solve King Altman. And do you want me to solve more problems in King Altman, different examples, more complex examples, or do you think you can take it up from there? Here, you'll solve other King Altman. So you need to give me feedback, and then we will solve more King Altman problems, bye-bye, ping pong, so many other things. They tend to become more and more complex as you have more and more complex reaction mechanisms, and they tend to become tedious algebra in terms of algebra. But the concept remains rather simple and straightforward. So while it is tedious algebra, it is actually not something which is difficult to apply. Is this clear?
Oh, yes, sir.
So but when you give me feedback, I will decide whether we do more King Altman or not. So,
Sir?
that is it. Yes.
I think, sir, you give us the problems and then we will solve it, and we will not be able to solve. Then we will come
It is there.
to.
तो भाई वो तो मुझे सबसे आसान है. बाय बाय का करिए. बाय बाय का करिए. इसी प्रॉब्लम में इरिवर्सिबल करिए, जो कि आसान है. एक कठिन सा करिए रिवर्सिबल, या बाय यूनि रिवर्सिबल करिए एक. आई थिंक ये 2 कर लेंगे, काफी है. और ऑर्डर ही रखिए आप लोग, कम से कम ये 2 करिए आप लोग. बाय यूनि रिवर्सिबल करिए और बाय बाय इरिवर्सिबल करिए. 2 बहुत ऑब्वियस मॉडिफिकेशंस हैं. These are 2 very obvious modifications of the problem. If you can solve it, I think you'll be able to solve everything, because this, and don't solve it to the end. I mean, it'll become tedious. A lot of things, for example, in a lot of things get cancelled out. You will discover that a lot of, terms in the denominator tend to cancel out. Okay. That is why I'm not doing it. You will have a very long denominator in a by-by reaction, because the by-by reaction would be like this. And so there will be this, and there will be this, and there will be, this. Oh God. And there will be sort of this. And what is the 4th one? See, this one is gone, this one is gone, this one is gone, and of course, this. In a that is by-by. In a bi-uni reversible, unlike what I did, you would have this, and this. This. But now this reverse is working all the time. So these 2 things which disappeared in EAB and once in EA would no longer disappear. Does it change the format of the equation? Is the question that one is asking. So obviously it changes, because now notice that EAB will now have terms which will contain not just AB, which was there in the denominator, but also terms of A and also terms of B. So solve it and check it out. This is the first set of questions that I'm giving you. Now, people are asking me to write it out. I'm not going to write it out. It is part of the lecture. If you listen to the lecture, you will be able to create problems of your own. Okay?
Yes, sir.
Okay. So now let us do the second problem and the general impressions. What was the second problem? The second problem was actually very simple. It was basically saying that you have a metabolic reaction, actually A to B to C to D, which is actually, I didn't say it so much. And suppose we are focusing on B to C, so we are not really bothered about these things. But in general, the conceptual problem is much more interesting, and you will come across it if and when you do your metabolic regulation problems. So these are all have values beyond the course. So that is one of the purposes of teaching you this. So now suppose I have an inhibitor, which is a competitive inhibitor, and this problem was actually more important because I did not give it. But suppose you have, instead of competitive inhibitor, you have an uncompetitive inhibitor. And really the question is, which of these is a superior inhibitor? Now, and you can actually demonstrate that competitive inhibition is actually inefficient compared to uncompetitive inhibition in terms of slowing down this reaction. Why? Because the moment you add competitive inhibitor, you tend to increase the concentration of B. Of course, with both cases. But what is the sensitivity of this reaction when there is inhibitor present? And that is the question that I talked in the class, and you have to go back and think about it. So now with competitive inhibition, EV by S, and that is there in the book, so I'm not going to write it out, was what is it? 1 plus I upon 1 plus I plus alpha. Is this right? And EV by I is of course minus I upon 1 plus I plus alpha. Where I is, and this is given in the book, so I don't see why there should be a problem. That's why when Debriya said that, we have not practiced these problems, it's a bit odd, because this is I is nothing but I upon Ki, and this is again given in the book, and I taught this as well. So the first problem was also taught, this has also been taught. That is why I would request you to attend classes, S by Ks, and of course both of them are equal to 1, this is equal to 1, this is equal to 1. So this is actually 2 by 3, and this is obviously minus 1 by 3. Not much of mathematics here. And the Lin-log kinetics also was taught in the class, so that is that V is equal to V naught 1 plus summation actually, summation E V by Si, ln, instead of delta S, ln Si upon Si naught, something like this. Is this all right? And so here it is not Si but I and S. So this is actually nothing but V naught into 1 plus 2 by 3 ln of S increased by 2%, so it's 1.02 upon 1. And this is minus 1 by 3, so minus 1 by 3 ln of 1.05, 5% increase by 1. And that is the fractional change. And now, I'm sure you know that ln 1. This is actually 2% ln and delta S. See, ln S by S naught, Si naught, Si by Si naught is also equal approximately, for small changes like this, delta Si by Si naught. But you can always use a calculator. But this approximation is actually better than this approximation for reasons that I will not explain. So using this, instead of using the log approximation, the linear approximation is delta Si by Si. So if you use this, you get poorer results. If you use this, you get Lin-log. This is Lin-log, this is Lin. Right? So you practice these problems with different. So suppose I have two substrates, three substrates, competitive inhibition, non-competitive inhibition, uncompetitive inhibition. All of these have E values, and they're there in the book. You don't have to derive it again and again. And then plug it into these numbers. And then you can find it out. And so this will become equal to some V is equal to some V by V naught, the fractional change, V by V naught fractional change will be 1 plus, and ln 1.2 by 3 into, 1 point, ln of this will be what? So 0.02, no, maybe it will be 0.0198 or something. I don't really care. Minus 1 by 3, and this will be point, say 0.498 or 8 or whatever. I mean, I don't know what it will. It will not be 0.05. It will be slightly lower, and that is the small advantage that actually makes these predictions far better. And so it's important to remember that this, when you have when you had say 1.1, then it'll be not 0.1 but 0.09, and so that is how these numbers get more and more accurate in terms of predicting the new V. And so this is of course simple arithmetic, and you can see that the change in V naught is not 5% with increase of 5%, because this impact is, so that is the whole point of computational innovation. This impact is much lower, and this impact is higher because EV by S is much larger than EV by I. So you're increasing this 5%, and this is leading to 2% increase, but this fellow is contributing equally much to this. So really you will see that there is hardly any change. And that is what I wanted you to demonstrate. That you will see that 2 by 3 into 0.198 and 1 minus 1 by 3 into 0.049, and the velocity has not reduced at all. So maybe it is less than 1%. So really the purpose of this question has been lost because of people not doing it. But the purpose is to prove that competitive innovation is a bad innovation. If you did the same thing with a 5% increase and same values, or with uncompetitive, that is what I actually wanted to give, but I thought it would become too lengthy, then you will demonstrate that V by V naught has changed much more significantly. So do it with different inhibitors. Use these basic equations, Lin-log kinetics. Do it with algebraic, the power law approximations. Do it with linear approximations, power law approximations, and Lin-log approximations, and show me what are the values you get, and give me a guess as to which values are better, which approximations are better. Point number one. Point number two, far more importantly, how do these change V to V naught when you have inhibitors being added, because of which substrate concentrations tend to go up? This is the real question. So you have a lot of questions associated with this which are possible. One is different kinds of inhibitors, and how sensitive is the rate of reaction to a competitive inhibitor to an uncompetitive inhibitor. How sensitive is it to the substrate concentration? So you notice that EV by S is actually larger quantitatively than EV by I. And therefore, and as we increase I, if I was larger, suppose I had a very large value, instead of, let us say this was 2, and this was 2, or it was 4. Then you notice that EV by S becomes even larger and EV by I becomes even smaller. Because 1 plus I is now 1 plus 4 upon 1 plus 4 plus 1. And this is minus I becomes that much smaller. So this is the kind of problems that we need to sort of understand, and why these questions are being asked conceptually is very important. So put in the numbers, plug in the numbers, change I values, change alpha values, and show me that actually competitive innovation is a very bad set of innovation, because if I already have an inhibitor, the system becomes less and less sensitive to increased inhibitor concentrations. These are the kind of questions that you need to understand. Is this clear? Can you solve this for power law? Can you solve it for Lin-log kinetics and for different kinds of inhibition? And prove that uncompetitive is better than competitive? These are the kind of problems you have to solve. So did you people solve these two questions? No. Yes. You can say no or yes, it doesn't really matter.
No, sir.
हाँ, तो ये आप लोगों को क्लास में पढ़ाया गया है, लेकिन आप लोगों ने थोड़ा ध्यान नहीं दिया। और ये देखिए, इसमें कहीं पे भी कोई इतना अलजेब्रा नहीं था जो कि आप लोग which you could not have done. You know, it was not a difficult problem. I mean, as I said, I have avoided giving the more complex and difficult problems. Even in the lab question, I think I don't remember the lab question. What was it? I said that VA, that was also about inhibition, competitive versus, and I said solve it graphically. So let us sort of draw it like this. So this is your graph. 1 by V versus 1 by S. And I just wanted to know whether you understand this. So this is your plot. And for competitive innovation, this is your plot. Right? So for competitive innovation, this is your plot. So suppose you are operating at this point. I'm choose some random point here. This is the point that you are operating at a substrate concentration S. Now S is doubled. So this is the normal equation for no inhibitor. This is 1 by V versus 1 by S. So this is the velocity at this substrate concentration. Some qualitative drawing, no inhibitor. When I add inhibitor and I add competitive inhibitor, if I add competitive inhibitor, I know that my line will be like this, right? Because the 1 by V max remains the same, but the slope here is Km by V max. Slope is Km by V max and Km increases. So slope is Km by V max, so the slope will increase, right? So obviously notice that at this substrate concentration, this is the velocity. At this substrate concentration, this is the velocity of VA. Let us assume that VA is the competitive inhibitor. Notice that this velocity is lower than V naught. Right? And notice that at S is equal to twice S naught. And so it is just a matter of graphs, and this is something which has been taught to you. Notice that and this obviously, this point here, because V is the same, notice that V is the same, is 2S naught by definition. That is why it is equal. You realize it is 2S naught, so V is equal to V naught. So if you draw a line like this, you go towards same V. If you draw a line like this, you go towards same A. So this here at 2S naught, this V is V naught. This is V naught, which is also equal to VA star, is also equal to VB star. So now this is VA star. Notice same velocity as V naught, but substrate concentration double. But it's also equal to VB star. But notice that VB star, the line has a slope like this. So this is also VB star. So the line has to pass through this point. But also remember that this line has to be parallel. This is the line that you will draw for uncompetitive. And many of you have drawn this, but you've not thought about it. So now notice that it has to pass through this point because they at 2S naught, VA and VB are both equal. So this is VA and this is VB for competitive, and this is VA is competitive. So now you can tell me this is V naught, highest velocity, VB lower velocity, VA even lower velocity. Both of them, all three of them, I mean when they are double, so notice that VB uncompetitive is actually having a higher velocity than VA, but still lower than V naught. So when you have uncompetitive and at 2S naught they have to become equal, then this has to be here and this has to be here. And this is a graphical explanation of what you are supposed to have done. You're supposed to have drawn parallel lines and lines passing through 1 by V max. So this lines, competitive inhibitor has to follow like this has to follow parallelly. And this is all. So is this something which has not been taught? It has been taught. But you have to think about these things. You have to think about the fact that these points. So this is highest velocity, lower velocity, even lower velocity. At this point, so two lines from V naught, one line parallel to the x-axis and one line parallel to the y-axis. So did any one of you do this? No. So this is my worry. This is my real worry that you have to, I mean, this was not an algebraic problem. This was a graphical problem. I believe that, I mean, your ability to handle graphs and conceptually handle graphs is as important as being ability to handle differential equations and algebra, because today graphs and understanding through graphs is equally important. So this is the way you solve this problem. So now tell me, how would it look for a non-competitive inhibitor? If the non-competitive, if I had said non-competitive inhibitor has the same value as the slope here, where would it go? So now you have to remember that this line here, this is the original line. So remember, this was the original line here. And this line here, remember, non-competitive inhibitors meet at the x-axis, unlike the competitive inhibitors which meet at the y-axis, and uncompetitive which are parallel. And so the line that you will draw, and now this is a poor drawing, but you know, will be like this. Again. So what about the non-competitive case? The non-competitive case would be like this. So it would go, it would not be parallel, but the slope would be less. So it will be somewhere here in the middle of VA and VB. Can you make that out? Yes, no, because I'm drawing it poorly. Hello? Can you hear me?
Yes, sir.
Can you make out where the non-competitive one will go? This line? This line, the non-competitive slope is higher than the slope of this line, the ordinary slope. It is this line, the uncompetitive has the same slope. The VA has the highest slope, the competitive has the highest slope, and the non-competitive has an intermediate slope. And so it will cut the x-axis at this line, S is a constant, at somewhere in between VA and VB. Yes? No?
Oh, yes, sir.
कोई बाकी लोग भी यस बोल रहे हैं कि सिर्फ रत्नेश के हाँ पे हाँ मिला रहे हैं? Okay. Aishwarya, there are just 4 people left. Depriya, Snehadeep, any responses?
No, sir, we understood.
You understood? So this is how you actually solve these problems graphically. What happens? Suppose I had put 3s naught. Suppose I had said at 2s naught the value is 1.5 times less. Then you have more complex issues. That is why I made it equal, so that you can sort of just draw a straight line and say, well, this is the line where it bifurcates, and then we can draw. So one line drawn parallel to x-axis, one line drawn parallel to y-axis with different graphs, and then your problem is solved. So you know, these are natural extensions of the fact that whether you have understood the 1 by b versus 1 by s graph. How would this graph be more beautiful or more interesting or more difficult with an Eadie-Hofstee plot or with a Haynes plot? That is another question that I want you to think about. I want you to think about non-competitive. I want you to think about how these plots would look in a Haynes plot or an Eadie-Hofstee plot. See, these are questions that are very interesting because, I mean, graphical playing around is a very interesting job. For example, I mean, a lot of people, and I've asked the question on error also. I mean, a lot of people can make this plot, right? I mean, this V versus S plot. I mean, and I ask you these questions now. V versus S plot. You have a plot like this, right? And suppose I made a plot like this, and I drew an approximate line through some data points, which were sort of randomly here, there, etc., etc. You know, I have, and obviously you notice that data points here are very, very worthless, and data points here are much more worthwhile, right? So that is also important. How do you choose data points? You never choose data points near saturation because your V values are all equal. But here V values are changing significantly. Now, a lot of nice, clever algebra has been done. Suppose you have this plot and you can make this plot somehow. Now, one of the questions is to say, what happens if I draw a tangent to this point at 0? And then they say, well, hold on, tangent drawing is very difficult. How about drawing a tangent? How about drawing a chord which cuts this line at V is equal to 3 by 4 V naught? What is the slope of this line? And can that line be used to determine experimentally what is V max and K? These are simple algebra plus graphical, coordinate geometry. What happens when I draw a line B is equal to with a chord? These are chords which cut this red line. No, I've made it black. Sorry, this red line here at V is equal to 3 by 4 V naught, at V is equal to 2 by 3 V naught, at V is equal to 4 by 5 V naught. And what are these slopes of these chords? Slopes of these chords. And can these slopes then be used to determine V max and K? Notice that the tangent here has a slope of, what is the slope? V max by K. I hope you know this. But what about the slopes of these lines? Theoretically and logically, these are extensions of the standard Michaelis-Menten kinetics problems. And these are things that you should be able to handle without actually giving. So please solve these things. Please solve, find out slopes of these lines, of these chords, and tell me how does this line look like. And we will draw many more graphs of simple Michaelis-Menten kinetics, and each of these graphs is relevant. So let us not just be stuck with simple problems. So it is important to understand this very simple zeroth order equation and all the games that you can play around it to be able to determine the two very basic parameters, Vmax and K. Can you think of other methods? We have talked about Helm's plot, Eadie-Hofstee plots, but there are hundreds of other methods that are available, and I will try to do it in the next class. And not teach you other things now. No more new stuff. Let us just focus on this simple equation V is equal to V max S upon K plus S. And I want to ensure that you have understood all the intricacies of this rather simple equation, which is just first order kinetics followed by zero order kinetics. I mean, I'm sure you would have done this in bioprocess technology. Have you heard of something called Blackburn kinetics, which is like this?
No, sir.
No, sir.
Huh? This is zeroth order, first order. This is an approximation of this equation. Of course, there is a maximum error at S is equal to 2Ks. Turns out that this is called Blackburn kinetics is much more easy to model in a computer, because from S less than 2Ks it is first order, and S greater than 2Ks it is zeroth order. And it turns out that this kind of very simplistic modeling, where this is first order at S greater than 2S and S greater than 2, it actually helps in a lot of differential equation solving. Because working with this kind of equations, I do not know whether you are aware of stiff differential equations. You are aware of stiff differential equations? You are aware of stiff differential equations?
No, sir. No, sir. No, sir.
Basically, stiff matlab, the numerical irritation, flows and overflow mechanisms of numerical calculations becomes very nasty, and they do not converge. And those are stiff differential equations. And in my time, we used to use Nagilev subroutines to solve stiff differential equations. Now there are much better techniques to solve differential equations which are stiff. But these kind of equations invariably lead to noise. And a Blackburn kinetics where S is less than 2ks is first order, S is greater than 2ks 0th order, is actually far more easily solvable in terms of data, with far less noise in the numerical solutions. So, so understanding this even in terms of enzyme kinetics or in terms of growth rate, what happens with saturation kinetics, 0th order when it's high, first order when it is low, is a very simple but also very interesting exercise. And you need to look at various options. Okay, so now this was the solution to this, and then of course the other questions were actually simple, but I should answer them for you. For example, I said TNF alpha. What was the first one? I think TNF alpha. And so obviously the question really was more complicated. I simplified it. Suppose you have a pH optimum in terms of stability. So you should always work with enzyme purification at the point of pH where the enzyme is most stable. So it is not that Pi is equal to say 6, then I should work with either anion or cation. So this much at least people should have understood. I found it very odd that even here people. So pH is 6. So any pH above 6, say 7 or 7.5 or 7 or 8.5 or whatever, you will have more and more negative charge. And any pH lower than 6, say 5 or 4, you would have a positive charge, right? Because your pH is lower than Pi. So H ions are there, so the protein has a positive charge. And if you have a positive charge, then you use an cation exchanger. And if you have a negative charge, you use an anion exchanger. This is something which is obvious or known to you. I am not sort of registered till it is done by you. And therefore, you can, for TNF alpha, which has a PI of 5.79, you can either choose 4 or you can either choose 7. But which one will you choose? A cation with 4 pH or an anion with 7.5 pH? Obviously, you will choose the pH where it is most stable. There's a stable protein during purification. If you choose 4, you can use a cation and use 4, but you will end up degrading the protein because pH 4 here it is highly unstable. And so it is for pH 9. So you choose a pH which is the best, and if it is far away from your Pi, which it usually is, then you choose the ion exchange. So your ion exchange choice is actually determined first by the stability, and that is really common sense, and then choosing the ion exchange, and then that pH, choose that pH for working, and then see whether it is positively charged or negatively charged, and then moving ahead. So you will also not choose a pH of 9.5 just to be far away. Neither will you choose 4, which is far away. So you'll choose the pH where it is most stable. Right? So what was the other questions? I don't even remember, and we are running out of time. I think, you remember any of the questions? Well, one trick question, I think the last one was when I said V is 10% error. Now, V has a error of V naught plus minus 10%. Now, usually this is not true. Usually this is not true. And I wanted to sort of say this, that usually the error is V naught plus E. If the error is V naught into 1 plus E, these are two different kinds of errors. And when the error is like this, which is usually the case, this is hardly the case. Under certain conditions, if this is the case, then a plot of 1 by V tends to become very high when E is a constant, and so for small values of V, small v, your E dominates in this 1 plus V by E. Obviously, that's logical enough. When E is small, you are actually plotting 1 upon E. But if the error is 1 upon V 1 plus E, then you are actually not bothered. So if it is proportional error, you can actually make a plot of 1 by V versus 1 by S without trouble. The problem is, and that is what I wanted you to say, the problem comes when the error is a constant, which it usually is. So I deliberately sort of made a trick question which was unfair, that I said the error is like this. In which case, the error will be the same. But if you had an error like this, your errors would tend to be, sort of go up and up and up and up. So they would tend to increase. Because E is a constant. So for Haynes plot as well as the double distributed plot, if your error is like that, you can take reciprocals without too much trouble. So that is one thing. The other problem of immobilized column, I think there was one question on immobilized column, which really has to be remembered that, you know, as you change the flow rate, you have to sort of remember that you cannot impact, and this is something again I mentioned in the class, you cannot impact on the internal diffusion, but what you can do is work on the external diffusion. So the external diffusion, and you have to also remember that this external diffusion, this dA and the diffusivity constant dE on the film is actually a function of velocity. So this is the most important statement that you have to make, that this is a function of velocity. So as you change velocity, which means you change residence time, you can actually end up having at lower velocities a high. So the plot is, again, I mean, I didn't teach too much of chemical engineering here, but the plot is like this. So as velocity increases, the diffusivity rate goes down. And so you have to have a high velocity to ensure that your external mass transfer is not controlled. So when you reduce velocity and your external mass transfer is controlling, you have a bad design, you would have to actually ensure that you either have a taller column or otherwise you will have problems of lesser conversion, even though you're giving more residence time because of external diffusion becoming rate controlled. So let us stop here, and next class also we will work on problems. We will just pick up problems to start from the very basics. V is equal to V max K, S upon Km plus S, and actually solve problems. We'll go on to internal mass transfer. I wanted to solve a problem, very simple. Take take a CSTR, take D values and S values. Sorry, let us sort of another homework problem for you guys. Please solve this problem. Is it time? 2 minutes? Yeah, 1 minute just. Take a CSTR, put some knobs here, etc. So let us say R is equal to 2 millimeters. And say that take some D, take some S, and make a plot of D versus S. And tell me what is happening here, and tell me what happens if I reduce R to 1 millimeter. How will the S output change, S star? That is all this is the question. The question is, if an R is equal to 2 millimeter, at different dilution rates, I get different values of S. What will be the S values if R is equal to 1 millimeter, but the number of beads is now 1 cube, 8 times more. Let us say there are 100 beads here of 2 millimeter, and now I put 800 beads there of 1 millimeter, so that Vmax is the same amount of enzyme. Tell me how the S values, output values will change if I have a plot of D versus S. Can you do this? Think about it. These are the kind of problems that you need to solve for, say, I'm giving an internal diffusion, external diffusion also similar problems can be constructed. So let us stop here, sit down and solve problems. Okay?
Yes, sir. Thank you, sir.
Okay.